Hi, everyone. Sorry, I am not able to, be here today. So, what I'm going to try to do is take you through the information as if I was here. So, we're going to do the notes together, and then I'll have a video that'll be linked within the lab for you to see what's occurring in those reactions. So, today is really just an extension and a wrapping up of what we've been doing on Monday and Tuesday. Hopefully, you got a chance to try the double replacement reactions on mastering either Tuesday night or Wednesday night. If that's not true, try to get those done as soon as possible. And today in class is a great chance to do that. Also, remember this reaction balancing worksheet. That's the back of Monday's notes. If you haven't had that checked by me yet, then it's in as missing. That will become a 0 at the end of this week. So let's get that knocked out. But first, want to wrap up our double replacement notes. So right here, this is what we were doing on Tuesday. We looked at how we trade our partners, sodium going with the acetate, so our cation to the anion, lead going with the sulfate. So on a double replacement, like this general formula here, we just swap our cations and swap our anions until we have our new compounds. Our charges are balanced, our formulas are based upon those charges. So we wrote all of these out, and then we looked at, well, what's really happening? When I mix chemicals, the new thing that I'm making, barium sulfate and potassium nitrate, or sodium sulfate and potassium nitrate, might change significantly, might look different, might act different, and make that cloudy white solid, or it might do nothing. And that's why we looked at this set of rules to tell us what are the things that normally form a cloudy white solid. Those are insoluble things. Or what are the things that normally just sit there and dissolve and kind of act and look boring? Those are soluble, or we say that they stay dissolved and are aqueous. We practiced this a little bit. We were looking at the different rules. Well, if it was in rule 1 or 2, no matter what it's bonded to, we are going to be dissolved. If we're in rule 3, we dissolve most of the time, but just a few exceptions. Rule 4, we dissolve most of the time with even more exceptions. But once we get down to carbonate, phosphate, chromate, sulfide, and hydroxide, we're almost always going to see insoluble, and those things would be solids. So almost all of my phosphates are solid. A lot of my sulfates, but not all, are solid. My acetates are all aqueous. And then with the chlorides and the bromides, we have a combination of the two. So we practiced that. Today, we're talking about what that actually looks like in the liquid, because it's not sodium and sulfate that are actually bonded. What they do is they dissolve or they dissociate. The ionic compound breaks into its cation and its anion when we put it into water. So if I had sodium chloride, I don't have salt molecules floating around. I have sodiums and I have chlorides. When I have calcium nitrate, I don't have calcium floating or calcium nitrate molecules floating around or formula units. I have calciums and I have nitrates. So the first thing to recognize is when I have magnesium chloride, that's not what floats around. It floats around as magnesium ions and as chloride ions. Potassium phosphate, I turned that into a formula, and it floats around as potassiums and as phosphates. So here I have pulled up a simulation that shows what that would look like. So when I shake my salts in with my sodiums and my chlorides, they break apart. I get one sodium for every one chloride. Or if I put something like calcium chloride in, it still breaks apart. I get cations, my calciums, which are my darker green plus ones, but I get two chlorides for each of those. So with each of these different things, I have cations and anions, and they break apart. A polyatomic ion like nitrate is still just one ion. So those would stay together. So I get a sodium for every nitrate. Here it has some other things there, but the key idea is whether it's a 1-to-1 or a 1-to-2 ratio, and that comes from the chemical formula. Magnesium chloride was 1-to-2. Potassium phosphate's 3-to-1, which is why I have a 1-to-2 and a 3-to-1 formula there. Down here, we are starting to draw what this actually looks like. When I have magnesiums and chlorides and potassiums and phosphates, they are not floating around in molecules. We have Ks separately floating around and phosphates separately floating around. The first thing I did was balance. Because this had a 3 on my magnesium, I threw a 3. Because I had a 2 on my phosphate, I put a 2. And that 3 and that 2 led me to know that I had to have a 6 and a 1. The pictures might even help even more. I have 3, boom, 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 magnesiums here to account for the 3 magnesiums in that formula. I have 6, 1, 2, 3, 4, 5, 6 chlorides floating around, which corresponds to these 6 chlorides. Sorry about that. Google doesn't like me, but we're still going here. And then we can do the same with our potassiums or our phosphates. When something was a solid, the thing that was the solid was the magnesium and the phosphate. We would need to use our solubility rules to recognize that. But that formed a solid, and these were labeled as AQ, AQ, AQ because they are soluble. So what I did with my soluble ones was recognize that they actually do dissociate. Magnesium chloride doesn't look like 3 mgs, MgCl2s. It looks like 3 mgs, boom, 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 and 1, 2, 3, 4, 5, 6 Cl minuses floating around. This is sometimes called a complete ionic equation or a complete ionic drawing. We show all of the ions the way they actually looked. For aqueous, we break them apart. We show all the ions the way they actually look. They're aqueous, so I have 2 times 3, I have 6 potassiums, and 2 times 1, 2 phosphates. But then, just like we're going to do in the lab, just like I did in the demo, we pour them together. Now everything on this side's in the same beaker. The potassiums are still floating around, the chlorides are still floating around, but the magnesium, when it went with the phosphate, when my outside things went together, that made something an insoluble solid. Each of these next ones has that same idea. We swap partners, sodium to nitrate, we've got that, aluminum to carbonate, we've got that. Then we have to think about sodium carbonate with a 2-to-1 ratio right here. Aluminum nitrate, a 1-to-3 ratio. Sodium nitrate, a 1-to-1 ratio. Aluminum carbonate, a 2-to-3 ratio. So my subscript on each of these is based upon the charge on sodium, +1, -2, +3, -1. And then we use the same charges, but often end up with different subscripts on our product side. I went down the line. Anything with sodium, rule 1, is soluble. Anything with nitrate, rule 2, is soluble. Anything with sodium or with nitrate, rule 2 and 1 is soluble. But rule 5 says my carbonate will be a solid. From there, I think about how many sodiums are actually bouncing and banging around. 3 times 2, there's 1, 2, 3, 4, 5, 6 +1 sodiums, and 1, 2, 3 -2 carbonates. There's 2 +3 aluminums and 6 -1 nitrates. The 6 sodiums and the 6 nitrates are still just floating around as we make one of my aluminum carbonate molecules or formula units. We go through this whole process, swap partners, think about charges to write 1, 2, 3, 4 formulas, balance it with coefficients, often 1s, 2s, 3s, maybe all the way up to 6s. We've seen that a few times. Then we look at aqueous and solid. Very similar, if you didn't do it yet, to the last question on the mastering. You write the formulas, the formulas, the formulas, the formulas as we're swapping those partners. And then we use the solubility rules for aqueous and solid. So the last one to kind of show it all at once with the rules: barium nitrate, barium's +2, nitrate's -1, cesium's +1, sulfate's -2. Barium's +2, sulfate's -2, cesium's +1, nitrate's -1. That's how I get formula, 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 balancing the charges. I go straight across, one barium for one barium. Two nitrates help me know that that should be a 2. Two cesiums supported that that should be a 2. And then my sulfates are balanced. Right down here, because I have NO3, that is soluble or aqueous. Because I have cesium, an alkali metal, column 1, that is aqueous. Barium sulfate. Sulfate is rule number 4. It should have been soluble, but in this case, it's with barium, so it is insoluble. That's how I knew my solid. Rule 1 and 2 tell me that those are both aqueous. Because it was a 1-to-2 ratio, just like in my simulation, I had 2 of these and 1 of those, a 2-to-1 ratio, 2 of these, 1 of those. Over here, I've got 1, 2 cesiums, 1, 2 nitrates, and then my solid. While they are floating around, they have charges. Only when they are together and the positive and the negative are equal and opposite have we made something that is neutral without a charge. So once again, the key here, which we'll practice again on the lab, and we've got the answer keys, are that our ionic compounds break into cations and anions with charges. But we go through the process by swapping partners, looking at charges, and we're going to draw them down here anyway, so we need to know them. Looking at the charges to put them together, we count each thing, magnesium, and compare it, chlorine, and then compare it, potassium and phosphate, one at a time to balance them. We look at the solubility rules. They'll be given to see, is it solid or aqueous? Often, and really always for us, you'll have 2 aqueous to start with, and pretty much always 1 aqueous and 1 solid on the other side. So this just takes that repetition and practice. The mastering does it really well, but we'll also practice this in class on Friday, and the lab is going to have you go through it as well.